Today we will be going over the concept of predicting base strength. Now before that, let's go over some common values of pKa. For example, as you can see, we have sulfuric acid, hydrochloric acid, hydronium, acetic acid, ammonium, water or methanol, ammonia, and methane. Now these values can be used quite often, therefore I'm going over them in this video. For example, the pKa value of sulfuric acid is -10, of hydrochloric acid is -7, hydronium is approximately -2, acetic acid is approximately 5, ammonium is 9, water or methanol is approximately 16. They both have approximately 16. Ammonia is 35 and methane is 50. Now the reason I went over these values is because if you see a similar molecule which has some characteristics which resemble one of these molecules, you can predict its pKa to be close to the value that I have stated. For example, if you had a molecule such as this, now what does this molecule resemble with, right? Where can you see something similar? Well, on this screen, you can see that this part of the molecule looks quite similar to the hydronium. Therefore, you can say that the pKa of this molecule will be approximately -2. Although it might not be exactly -2, but it will be close to this value. So learning these values are quite useful when you deal with acid-base reactions, or when you want to predict the pKa of something similar to one of these molecules. Now, we will be going over the conditions which we see when we predict the base strength. There are three conditions. First is resonance. Whenever you have a molecule that can undergo resonance, it would be a weaker base because the charge can get distributed over the molecule and there would be less charge per unit area. Number second would be the electronegativity. A molecule or an atom which is more electronegative can handle the negative charge more easily because it wants electrons, so it would have no problem working with the negative charge. So if something is electronegative, highly electronegative, and it has a negative charge on it, you can predict that it is pretty happy with that charge and it is stable and it will not react, therefore you can consider it weak. Third criteria is of size. Something which is pretty big can distribute charge much easily over its surface, and similar to resonance, it can be considered weaker base because the charge is distributed over a larger area this time and there would be less charge per unit area and less reactivity. Now we will be going over some examples which demonstrate these three conditions. Number one can be the hydrofluoric acid and its reaction with water molecule. Now this looks like an acid-base reaction and it should be pretty easy, and if you have trouble during this reaction, then you can go ahead and check my other video which shows you how to do acid-base reactions. So here, the lone pair on oxygen will go and attack the hydrogen which is on the hydrofluoric acid, and this will cause the bond between hydrogen and fluoride to break, and the electron will transfer onto the fluoride, and this will result into the fluoride ion and hydronium. You can check your reaction by conserving charge. The charge should be balanced on both ends. On the left-hand side, there is no charge on hydrochloric acid, no charge on the water molecule, and on the right-hand side, there is negative on fluoride, positive on hydronium, and negative plus positive is 0. So the charge is balanced. Now let's consider another reaction, but this time consider hydrochloric acid. And we have again the water molecule. The reaction is similar. The lone pair on oxygen goes and attacks the hydrogen. The bond between hydrogen and chloride breaks because chloride is more electronegative than hydrogen and wants to keep those electrons when the hydrogen goes away. And this will result in the chloride ion and hydronium ion. Now again, the charge is conserved. No charge on the left-hand side, negative and positive on the right, which is 0. Now, how do we know which molecule or which ion here, like out of the fluoride or chloride, which is a stronger base? Now, why I am saying it a base? Because they came from an acid. There was hydrofluoric acid, reaction happened, and you got fluoride. There was hydrochloric acid, reaction happened, and you got chloride. So whenever this happens, on the left-hand side, you have an acid. On the right-hand side is its conjugate base. Again, on the left-hand side, you have an acid, the hydrochloric acid, and on the right-hand side, you have its conjugate base. Similarly, you can say that on the left-hand side, you have a base, which is water, and you have a conjugate acid, which is hydronium. Now, how do we know which base, fluoride or chloride, which is a stronger base? Now, if you look on the periodic table, there is the column for halogens. The halogens are like fluorine, chlorine, bromine, iodine, astatine, and there is one more which we do not consider because it is radioactive. But if we leave that, even astatine is radioactive, so you can also leave that. But here, we're just comparing these two. Now, if you go down the column, the size increases. And what did we say about this condition? We said that if the size is big, the charge can be distributed more easily and there would be less charge per unit area, there would be less reactivity, and it would be considered a weaker base. So we can say that based on size, chloride looks to be the weaker base. But now you can ask a question that, wait a second, fluorine is the most electronegative atom we have, right? And if the fluoride has negative charge, it should be happy with it. So we can say, based on electronegativity trend, the fluoride seems to be the weaker base, right? Because it has the negative charge, it is happy with the negative charge, and it would be more stable with the negative charge. So based on electronegativity, we can say that fluoride is the weaker base. Now, which condition will be dominant? Generally, through experiments and through observations, we have seen that whenever you have two elements which come in the same column, like fluorine and chlorine here, size dominates. Because if you go down, size increases drastically. There is one more shell added to the atom, and that results in a much bigger atom. So the size is dominant down a column. So therefore, we say that chloride would be the weaker base. Now, if the base is weaker, its conjugate acid would be stronger. Means hydrochloric acid would be the stronger acid. Now that makes sense, right? Hydrochloric acid is one of the strongest acids we have. The pKa of hydrochloric acid, as we stated above, is -7. So it is -7, and a pKa which is negative means it is a strong acid. Now the hydrofluoric acid, that is not a strong acid. It has a pKa of +2. Now being an acid and having a pKa of positive, you are not considered a strong acid. Therefore, our prediction is correct, right? We predicted chloride to be the weaker base, and therefore its conjugate acid, which is the hydrochloric acid, would be the stronger acid out of the two. So that is correct. Hydrochloric acid is stronger acid because its conjugate base, the chloride, is the weaker base. Now we can go to one more example in which we consider another characteristic. So let's consider sulfurous acid. Now keep in mind this is not sulfuric acid, this is sulfurous acid, which is considered to be weaker than the sulfuric acid. Now let's see if our prediction says the same. So we will react it with water. Again, because we have an acid on the left, a base on the right, it is an acid-base reaction. The electrons on the oxygen, the lone electrons, they attack the hydrogen, and the bond between oxygen and hydrogen breaks, and we get hydrogen sulfate ion. And we also get hydronium. So again, the charge is balanced. Let's consider another reaction, but this time I am considering sulfuric acid. So actually, let me make this bond this way. So this is the sulfuric acid now. And always remember to draw your lone pair electrons. They're helpful. And we react it with water. Again, the lone pair attacks the hydrogen, the bond breaks, and you get an ion. And hydronium. And again, the charge is balanced. So now, how will we know which is the stronger out of the two? Now, if you consider here, these molecules, they have one condition which tells you that they can undergo resonance. So what is the condition for you to undergo resonance? The condition is you need to have lone pair, single bond, and a double bond. So do these molecules have that? They do. They have a lone pair, they have a single bond, they have a double bond. Does the other one have it? Yes, they have lone pair, they have single bond, they have double bond. So looks like they can undergo resonance. So let's see their resonance structures. Now, if you consider the sulfate, the hydrogen sulfate ion, what would be the resonance structure? To undergo resonance, this lone pair would come here and form a double bond with sulfur. And the double bond, the pi bond between oxygen and sulfur, would break and go on to the oxygen. And this would result in the following. So that is the two resonant structures. And now if you consider the ion which resulted from the sulfuric acid, it looks like it can undergo more resonance than the hydrogen sulfate ion. Let's see if that is true. So the lone pair comes down, forms the double bond. The pi bond between sulfur and oxygen breaks and goes on to the oxygen. And we get the following. Now, is there more possibility of resonance? Looks like there is. You have a lone pair, you have a single bond, you have a double bond. So it looks like it can undergo resonance. So let's see. The lone pair forms a double bond. The pi bond breaks, goes to the oxygen. And we get the following. So in sulfuric acid ion, right, the ion which resulted from the sulfuric acid, we get three resonance structures. And in hydrogen sulfate ion, which resulted from the sulfurous acid, we have two resonance structures. So it looks like charge is getting distributed more evenly over the sulfuric acid ion, the ion which resulted from the sulfuric acid. So we predict that this ion which resulted from the sulfuric acid, that would be the weaker base. Because this ion can undergo more resonance compared to the hydrogen sulfate ion, it can distribute its charge more easily, more evenly over its surface, less charge per unit area, and therefore it is the weaker base out of the two. Now, what does it tell about the conjugate acid then? That tells you that sulfuric acid is the stronger acid. Now, isn't that true? It is. The sulfuric acid is one of the strongest acids we have. The pKa of sulfuric acid is -10 as we stated above, and the pKa of sulfurous acid is 1.85. So it is true that sulfuric acid is the stronger acid. And how did we know that? Because its conjugate base was the weaker base. So therefore, it is very useful for you to know which is the weaker base. It helps you predict the reactivities in many different mechanisms. Now, I will give you a little hint on how to solve some reactions, and this will help you in many reactions, believe it or not. For example, if you have a weak acid, now these concepts are simple, but they can prove useful in many cases. So I'm writing some scenarios here, and you will find these scenarios in many reactions. So as you can notice, what I'm doing is just writing the two possibilities that we have for an acid or a base. If you have a weak acid and a weak base, none of the two is strong enough to cause anything. You will need to give energy to this reaction to make it happen. Therefore, we do not predict this reaction. We say, okay, you need energy for this reaction. It is not going to happen spontaneously. Weak acid and strong base, Yes, a reaction can occur because one of the two is strong. Strong acid and weak base, yes, it can occur. And strong acid and strong base, for sure it will occur. So these, though simple, will help you in many reactions. Now let's go over just one more reaction and then we will call it the day. So we have phosphine and we react it with water. Again, an acid-base reaction. What happens? The electron goes, attacks the hydrogen, the bond between phosphorus and hydrogen breaks, goes to the phosphorus, and you will have the following. Again, the charge is conserved. Now let's consider another reaction, and that would be between ammonia and water. Again, a simple acid-base reaction. Attacks the hydrogen, the bond breaks, and the electrons go onto the nitrogen. And what do we get? We will have this, a negative charge on the nitrogen, and we will have hydronium with a positive charge, and the charge is balanced. Now, how do we know which out of the two is a weaker base, right? Now, if you see on the periodic table, in the column which has nitrogen in it, you will see it will have nitrogen, phosphorus, arsenic, antimony, bismuth. These are the elements that will be there. Now we are just comparing these two. Again, it is just a column game, and phosphorus is bigger in size compared to nitrogen. Therefore, we predict this to be the weaker base. And therefore, we predict this to be the stronger acid. So phosphine is the stronger acid than ammonia. And if you compare their pKa's, you will see that it is true. pKa of ammonia is approximately 35, as it was in the table above, and the pKa of phosphine is approximately 27. The lower the pKa, the stronger the acid. So this was a basic tutorial on how to predict the base strength. Thank you for watching, and I hope you enjoyed it. Have a good day.